Alright, welcome to the walkthrough for Lab 6, Saturation and Atmospheric Stability. And we're going to talk about questions 1 through 16. And for question 1, they're asking you to look up the saturation mixing ratio from the same exact saturation curve table that we've been playing with, except for they've reprinted it into table 6.1. And so we're going to look up question A, and I'm going to work through 1A with you. So I'm going to change hands so I can write. So 1A, and we have some information given on 1A, which is that the air sample is 10 degrees C, and that the relative humidity is equal to 75%. So we have some ideas that we can do a mixing ratio on. And if I look it up on table 6.1, which this might be blurry and I apologize, and at 10 degrees I come up with 7.762. So 7.762, and that's going to be grams per kilogram, and that's my answer for 1A. Now for 2A, they asked me to find the mixing ratio. So we're going back to that equation we worked before. So 2A, I'm going to plug my information into the relative humidity divided by 100% times by my saturation mixing ratio. Will equal my mixing ratio. So I'm going to let's plug everything in. 75% divided by 100% times that by the saturation mixing ratio from my curve, 7.762 grams per kilogram. My percentage units are going to come cross out, and I'm going to get as my answer 5.82. 5.82 grams per kilogram. So that's my answer for 2A. For questions 3 and 4, you're going to plot on the curve. And for questions 5 and 6, you're going to mix this. And to mix it, it's very simple. You're just going to add together sample A plus sample B and divide by 2, and you're going to get the mix in between. You're going to get the mixing ratios. So you're just adding together the two samples' temperature to get the new temperature, and that's going to give you A for 5. That's going to give you answer to 5. And then for sample 6, you're going to take the saturation mixing ratios. So question 6, you're going to look up the ratios that you found before, and you're going to add them again. A plus B, divide by 2, you're going to get the in-between, and that's the new mixed ratio for your new mixed saturation ratio. Then you're going to get the actual mixing ratio that you found using the equations on 7, that's 2A that you found, and you're going to do the same thing. A plus B, divide by 2, gives you the mix. So you're basically repeating this process and finding this new air sample with the answers. Alright, so we're going to start talking about adiabatic cooling. And as a reminder, the dry adiabatic cooling rate is 10 degrees Celsius every 1,000 meters. And the book does a really nice job at showing you a graphic of how the air parcel rises and cools off. And they talk about the dry rate and what it stands for, and the abbreviation being DALR, dry adiabatic lapse rate. And then you go on to question 10, which asks you to calculate changes in temperature at 100-meter increments. And they show you this sort of like table starting at the Earth's surface, and they tell you that it's 35 degrees C. Well, if we know that it's 10 degrees every 1,000 meters, I can skip all the way up to the 1,000-meter mark and know that it's going to be 10 degrees colder. So I can say that this If this is 35 degrees, this is going to be 10 degrees colder at 25 degrees C. Now, since this is in an increment of 1,000 meters, and I was to break 10 up into 100-meter increments, there would be 10 in between, meaning that I basically can drop temperature 1 degree. So right here would be 34 degrees C, 33 degrees C, 32 degrees C, and so on and so forth. So work your way through question 10. All right, so for questions 11 and 12, they're giving you a table that looks like this with two separate parcels of air. You have parcel A, which is 28 degrees Celsius, and parcel B, which is 10 degrees Celsius. And abbreviations for this part is LCL, which is the lifting condensation level. That's the height with which dew point has been met. And then they talk about a WALR, which is the wet or moist adiabatic lapse rate. And that is varied. And they give you two sets. So for parcel A, your lifting condensation level is 1.5 kilometers or 1,500 meters in height. And they tell you that the wet adiabatic lifting rate, lapse rate, is 5 degrees Celsius every 1K. And then for parcel B, and that's part of 12, they tell you that the lifting condensation is the same height, 1.5, and that the temperature is 7 degrees C every 1 kilometer. And so working down on the table, I kind of made a fake table to help you out. So here's my surface temperature, and here's my 28 for parcel A. And for the first one, I'm going to drop for half a kilometer, not a whole kilometer. So I subtract by 5, and I get my 23. I'm going to subtract by 5 again for 1. I'm going to get 18. Subtract by 5 again for 1.5, and I'm going to get 13. And at 1.5, I've hit my lifting condensation level. So for my next rate jump, I want to go down by 5s every 1 meter. And so I'm going halfway for that step, halfway step. And so I'm going to go down by 2.5. So 2.5 and 2.5. And I'm going to continue that 2.5 up the table. For the parcel B that I'm going to be working on, I'm starting at 10 degrees C. Same thing, dry adiabatic lifting rate is 10 degrees every 1 kilometer. So if I'm going up halfway, I'm going up by 5. So this and this difference is 5. I'm going to subtract 5 again. Subtract 5. Then I'm at my lifting condensation level, the bottom of my cloud. I'm going to flip to my wet adiabatic lifting rate. And I'm going to go down by 3.5 since it's 7 degrees Celsius every 1K. So 3.5, 3.5. I'm going to do that all the way up my line. And that's how I work on questions 11 and 12 to fulfill table 6-2. All right, we're working on question 14, which talks about filling in table 6.3 on page 57. And just as a reminder for temperature understandings, the dry adiabatic lapse rate is 10 degrees Celsius every 1,000 meters, and the dew point lapse rate is 2 degrees every 1,000 meters. So on the table, which down below here, has the surface at 0, and then 500, and then 1,000 meters, and we have a temperature, which is regular temperature, at 30 degrees. And so at 1,000, I have to drop 10 degrees, so this here is 20 degrees C, and the in-between is halfway between 10, so it's 5. So this would be 25 degrees C. Over on this side, though, we're talking dew point temperature, and that starts at 14 degrees C, and it is 2 degrees every 1,000 meters. So at my first set of 1,000 meters, I have to drop 2, which makes it 12 degrees Celsius. And the in-between will be 13 degrees Celsius. And so you guys can finish up this table. All right, so for question 15, you're solving for the lifting condensation level, the LCL, and there is an equation to figure this out. And the equation works as follows. It is the temperature in degrees C minus the dew point temperature in degrees C, all divided by 8 degrees C kilometers. And that's because of the height, the altitudinal height. And if you want to know more about why this equation, you can read it on page 57, working it out with the standard troposphere height and why 8 degrees C for the kilometer set. If I needed to find this in meters, I would have to do the difference in my meter set. So to find my LCL, it would be equivalent to 125 times my temperature degrees C minus my temperature dew point degrees C, and that's how I would find my answer in meters for this variation. So this one's for kilometers, this one's for meters. For 15, you're solving it in kilometers, and I've worked out part A for you, and I plugged it in. So 32 degrees C minus the dew point temperature 20 degrees C divided by 8 degrees C per kilometer. The Celsiuses get crossed out. I'm left with the kilometers. I work that in, and I get 1.5 kilometers is my lifting condensation level. Now you guys can work on part B.